So, with this notion of linear independence of vectors and a collection of vectors that can span the space, we are ready to now define what is called the basis, right. We will just define what the basis is, but I am sure most of you would have taken for granted what the basis is from your undergraduate signal processing, right. When you say Fourier basis, you would have just taken it for granted what the basis is. Now we are formally coming to the definition of what the basis is. Okay. So, let us start with this definition. Let S be a vector space, let T be a set of vectors from S such that span of T equals S. If T is linearly independent, T is said to be the Hamel basis of S. You could even ignore the word Hamel if you would want to, just it is a basis, right. There are plenty of good examples for this basis. So, if you think of the natural basis, for example 1 0 0 0 1 0 and then 0 0 1, this is basically a natural basis in R3. Okay. And you can have one 1 and 1 minus 1 as the basis in R2. You can also have 0 1 and 1 0, you could, but you know I am writing it slightly differently, but we will see through these connections. You can have possibly infinite set of such bases. Okay. So, with this notion of what a basis is, we are ready to prove a theorem which says that if T1 and T2 are the Hamel basis for a vector space S, then T1 and T2 have the same cardinality. So, we will prove this result, and this has important consequences. If T1 and T2 are Hamel basis, we can make this plural. For a vector space S, then T1 and T2 have the same cardinality. From intuition you should get this picture, right. If I say it is a 2-dimensional space and my basis is say 0 1 and 1 0 or 1 1 and 1 minus 1, then likely I may not have 1 1 1 minus 1 and some x y which is going to be the basis for that, and that is what we need to prove it in this result. So we will start with the proof. Suppose T1 is this collection P1, P2 so on till Pm, and T2 is the set which is Q1, Q2 so on till Qn, and let this be two Hamel bases of this vector space S. So, the first step what we do is we express the point Q1 belonging to T2 as follows. So, we pick this vector Q1 in T2 and we express it using the vectors in T1. So, let us suppose Q1 is C1 P1 plus C2 P2 plus so on till Cm Pm. So, of course, we must say here that at least one of Ci's must be non-zero, right, because it is a definition of a basis, and let this Ci be say some C1, at least one of them to be non-zero, and let this be C1. So, now P1 is basically 1 over C1 times Q1, basically we are rearranging this in a different form, minus C2 P2 minus C3 P3 dot 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 minus Cm Pm. Okay. So, we pick a point Q1 belonging to T2, express it in this form, and at least one of the Ci's must be non-zero, and let that be this element C1, and then P1 is basically rewritten in this form, just rearranging this equation slightly differently. Now, since we have written it in this form, we can say that we can eliminate P1 as a basis in T1, and we can instead replace that with Q1, right. You see the idea how we are progressing, right. We pick one in T2, express it in terms of T1, and then we say just we can replace that vector, that basis vector in T1 with this new element. That's the intuition, or that's the idea, and we will see how we progress on that. So, this implies we can eliminate P1 as a basis in T1 and use this set Q1 P2 so on till P is Vem as a basis. So, now we have the intuition into the proof of this result. So, we will try this again. So, similarly we say some d2 is not equal to 0, I pick q2 which is written as d1 q1 plus d2 p2, just observe this change, q1 then p2 plus dot 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 d suffix m pm. So, this is how we wrote the representation of q2 in terms of our newly formed set of bases, right. So, now we do this elimination again, we say p2 is 1 over d2 times q2 minus d1 q1 minus d3 p3 minus dot 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 minus d suffix m p suffix n. So, now we have sort of gotten the trick towards doing this, right. So, now I expressed P2 in terms of the rest. So, we can eliminate P2 from the list, so that we have a new set q1 q2 p3 dot 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 pm to form a new basis set. So, we do this iteratively and we land up with q1 q2 so on till q suffix m spanning the same space as P1, P2 so on till P suffix m. So, we can also conclude that m is greater than or equal to n. In the process of this replacement, we can say that m is greater than or equal to n. Now, suppose to the contrary n is greater than m, right. Suppose to the contrary n is greater than m, then a vector such as q of m plus 1 which does not fall in this set, this is very important, which does not fall in this set q1 to qm would be linearly dependent with the set q1 to qm. I did all the replacement. On the contrary, I assume n is greater than m, then a vector such as qm plus 1 which does not fall in this set q1 to qm would be linearly dependent with this set. Now this violates that T2 is a basis, because we had T1 and T2 both to be the basis, and now we have a contradiction. So we do this in the reverse argument. So we started off with some element in T2 and expressing it in terms of T1 and then replacing that element in T1. So we do this, we can do this in the reverse argument. With eliminating Qi, and then we can conclude n is greater than or equal to m. In one side we said m is greater than or equal to n, and in the other side we are saying that n should be greater than or equal to m, and basically this implies is only possible if m equals n, and this shows that the cardinality has to be the same. So the idea is as follows: you have some m, some n. So once you assume that m is greater than or equal to n, for which you fix some m, fix some n, start replacing all these n's with what you have in the earlier set, and then you conclude that basically m is greater than or equal to n, because if otherwise if n was greater than m you would have this contradiction here. And in the second case you would follow the reverse argument by eliminating all the qi's and then conclude that n should be greater than or equal to m, but with these two statements they have to be the same, which would imply m equals n.